Okay, good afternoon, boys. Good afternoon, girls. How are you? Hope you are well. Hope you are safe. So this afternoon, we carry on with our math lesson, and then we will carry on with our probability class. We started probability a few lessons before now. So we'll carry on with probability in today's lesson. And then, before we carry on, my name is Sadu Jafaru Abdullahi, and then probability is our today's topic. And at the end of today, you should be able to understand and apply the addition rule. You should be able to apply the addition rule for a mutually exclusive event. You should be able to apply or understand the components of complementary events, dependent and independent events. When an event is supposed to be dependent, when an event is supposed to be independent, and to solve problems relating to the above mentioned. Okay. So we look at some of the identities, some of the formulas that we have, some of what we call the identities. That first one is the addition rule. The addition rule, also called the sum rule. That for any two events, A and B, the probability of A or B, the probability of event A or B happening is equal to probability of event A plus probability of event B minus probability of event A and B. So this is called the addition rule. That probability of event A or B happening generally is equals to probability of the first event plus probability of the other event only minus m. So this relates to the probability of two events with probability of their union and intersection. Okay, so now we're saying this relates to the probabilities of two events with their probabilities of their union and intersection. So union is when we have A and B. Union is when we have A and B. And then intersection we get when we have A. When our union is when we have A or B, and then intersection we have A and B. Right. But for an exclusive event, the rule then change. The addition rule then changes because an exclusive event will mean that when events are mutually exclusive, so that will mean that those two events will not be able to take place at the same time. When events are mutually exclusive, it's going to imply that those two events cannot take place at the same time, meaning our probability of the two events taking place at the same time equals to 0. The probability of the two events taking place at the same time, that probability equals to 0 because the two events cannot possibly take place at the same time. So say the rule then reduces. So this rule is special case of the previous rule. So now we're saying the rule then reduces our probability of A intersection B to give us 0 for an mutually exclusive event. So therefore, it's the probability of event A and B is equal to 0. And then that will reduce. So our addition rule now becomes what? Probability of A or B equal probability of A plus probability of B alone. Because probability of A and B is equal to 0. Okay. That is one. An addition rule for a mutually exclusive event. Of a complementary event. So the complementary rule, they have what the complementary rule. Complementary rule says the probability of not A is equal to 1 my probability of A. Again, the complementary rule says that what probability of not A is equal to probability of 1. Probability of not A equals to 1 minus probability of A. So not A, probability of not A is equals to probability of 1 minus A. So therefore, probability of not A plus probability of A will give you 1. Meaning the chance of an event happening plus the chances of an event happening plus the chance of an event not happening is equal to what? 1. Okay. So that is an addition rule. Okay. So now the product rule now. Talk about the product rule. So the product rule is applicable for an independent event. It's used when we're talking about independent events. That if when we're trying to find out if event A is dependent or on another event B. So for an independent event, dependent or an independent event, we talk about what? The product rule. For mutually exclusive, we talk about the addition rule. Okay, for mutually exclusive or non-mutually exclusive events, then we are talking about the addition rule. But for dependent and independent event, to determine if an event is dependent, two events are dependent or not, or independent, then we use the product rule. And the product rule implies that what? The probability of, for an independent event, probability of A and B equals probability of A multiplied by probability of B for an independent event. But for a dependent event, if two events are dependent on each other, if two events are dependent on each other, then probability of A and probability of B is not equal to probability of A times probability of B. Okay, so this is independent and the dependent rule. These are the identities we employ. Okay, now progressing from them, we must note here that just because two events are mutually exclusive does not necessarily mean they are independent. Okay, that if two events are mutually exclusive, that doesn't mean that does not automatically mean they are independent. They are independent. When two events are independent, that means the result of one event does not affect the result of the other. Then we say they are what? Independent. Again, if events are independent if the result of one does not affect the result of the other happening. The chances of one event happening does not affect the chances of the other happening. Then we say they are what? Independent. But if the chance of one happening will affect the chance of the other, then we say they are dependent. Okay. So we're saying that when events are mutually exclusive, that does not necessarily mean they are independent. So to test for independence, we try to test for mutually exclusive events, we try to prove that probability of A and B is equal to 0, that there is no intersection between the two events, that the two events cannot take place at the same time. So that is how we test for mutually exclusive events. So for a mutually exclusive event, what we know is the two events will not be able to take place at the same time, and their intersection will be equal to 0. Okay, and then when to test if if two events are independent, so we try to prove that probability of A and B is equal to probability of A multiplied by probability of B. Okay, so if probability of A multiplied by probability of B is equal to probability of A and B, then they are independent. Okay, so let's see more example. Example 1. Write down which of the following events are dependent and which are independent. So which of these events are dependent, which are independent? Number 1, the student council chooses a head student and then a deputy head student. The student council chooses a head student and then a deputy head student. So is that dependent? Are those two events, are they dependent or independent? Choosing a head student and then choosing a deputy head student. So there will be two dependent events, because the chances of choosing the first person as the head student, so the probability will have effect on choosing another person as the deputy, because the number of individuals there will be less. By choosing the first person as the head student, so you know, reduce the number of individuals that are present from which the deputy head student to be chosen. So that means the dependence of the event of choosing the head student is will affect the probability or the chances of choosing the deputy head girl at the head student. Okay, so we're saying the two events are dependent. Okay, because the number of individuals present, there will be less. Right. Number 2, so these two events are dependent. Number 2, a bag contains blue marbles and red marbles. You take a red marbles out of the bag and then throw it back. in again before you take another marble out of the bag. So 2 events here, taking bag containing what? Red and blue marbles. So taking the red marble out and then throw it back before you choose another marble. So the first event is choosing the first marble. The second one is choosing the other one. So because the first one was thrown back, so that means the result of the first one will not affect the result of the other one. So they brought 2 independent events. So event B, so in solution, so step 1 asks question, did the available choice change for the second event because of the first event? Did the available choices change for the second event because of the first event? So you ask the question, will the available choice change for the second event because of the first event? So for the first one, yes, because the selection of Ed students, there are fewer council members available to choose for the second head student position. Therefore, the events are dependent. And for the number 2, no, because when you throw the first marble back into the bag, they are the same number and color composition of choice for the second marble. Therefore, the 2 events are independent. I do hope you understand that. Next, number 2. A bag contains 33 yellow marbles and 44 black. A bag contains 33 yellow and 44 black beads. 33 yellow beads, 44 black beads. We remove a random bead from the bag. We remove a random bead from the bag. Record its color and put it back into the bag. We then remove another random bead from the bag and then record its color. What probability that the first bead is yellow? So what probability that the first bead is yellow? So to do that, we're going to first have to add this together, find the total number of beads, and the probability of being yellow will be 33 out of the total number 77. So 33 over 77 will be our answer there, which can reduce to 3 over 7. And the probability of that the second bead is black. So what probability that the second bead will be black? What probability that choosing the second bead will be black? So because we have to put the first one back, so that means we still have a total of 13 yellow and 44 black. So which makes the total as 77 again. So the probability that the second bead is black will be 44 over 77. Okay, 44 over 77, and that can reduce to 4 over 7. And then question 3, what probability that the first bit is yellow and the second bit is black? What that the first bit is yellow and the second bit is black? So first bit is yellow, we mean that what's yellow over 77, and that means times the second bit is black, that will be 44 over 77. And then we simplify that to find our answer. Again, what probability that the first bit is yellow and the second bit is black? So first bit being yellow is 33 out of 77. And then the second bit being black is 44 over 77. So we'll say 33 over 77 multiplied by 44 over 77. So that can be simplified, and then we get a final answer. And then the fourth one, are the first bit being yellow and the second bit being black independent events? Are the first bit being yellow and the second bit being black being an independent event? So to prove an independent event, so we prove that probability of the 2 events taking place equals to probability of A and B equals probability of A times probability of what? B. Okay, but in this case, we're going to see that is what? Independent. Okay, because the first ball was what? Was returned back. Okay, let's see the solution. First, the probability that the probability of yellow bit first. So that will be 3 over 7. That is 33 over 77. Okay. And then probability of the black bits second will be 4 out of 77. And probability of yellow first and black second. So when drawing 2 bits from the bag, there are 4 possibilities. So you can find what a yellow bit and then a yellow bead and then another yellow bead, or a yellow bead and then a black bead, or a black bead and a yellow bead and a black bead, or another black bead. But our question here wants probability of the first being yellow and the other one being black. So in that case, so probability of the first being yellow is 3/7, 33/77, multiplied by 44/77, and then that will reduce into 12/49. Okay, and then what probability that are the two events dependent or independent? To prove if two events are dependent or independent, as we just said, you need to prove that probability of A and probability of B equals probability of A times probability of B. So what probability of being of probability of yellow is 3/7. Probability of black is 4/7. Probability of black and yellow will be 12/49. Right. Since 12/49 is equals to that 3/7 times 4/7, then the event is independent. The event is independent. Okay. Right. Now, now when talking about without replacement, now the previous example we talk about the bit or the item bit being replaced, but in the event where we have the sample not being replaced, so how do we deal with such? For example, from a bag of 3 red and 3 green beads, we remove a random bead and record its color. Then without putting back the first bead, look at that, without putting back the first bead, we remove another bead from the bag and record its color. Okay. Okay. Now the question is, now what's the probability of the first bead being red? What probability of the first bead? What probability that the first bead is red? So if the first bead is red, then will be what? That probability of first being red will be is either the first one is red and the second one is red, or the first one is red and the second and the other one is green. So these two will be suitable for our answer. These two combinations will be for our answer. Again, the question is what probability that the first bit is red? What probability that the first bit is red? So first bit being red would imply that what? If either the first bit, if the first bit is red and the second bit is red, that's in one scenario. Another scenario could be the first bit is red and the other bit is green. So these are two scenarios that we're going to work with. So in that case, we're going to have the first bit being red, we're going to have 3 out of 8. And then for the second bit being red, the second bit being red is going to be 2 out of 7. Why 2? Because the first one was not being replaced. So that reduced the number of red bits to 2, and the total number of bits to 7. So that means the chance of the probability of the first bit is 3/8, and that of the second red bit is 2 out of 7. And if you simplify that, you will have what? 6 out of 56. 2 cancels into 2 ones into 84. Then 4 times 7, 56. That's 3 out of 50. 6 out of 56, and then that's 3 out of 28. Okay. Now, and then for the other one now, for the second chance, what probability of the first one being red and the other one being green? First being red will be 3 out of 8, and the second being green will be 5 out of 7. 5 because there are 5 green beads, but there are total 7 of beads now because the first wasn't replaced. So if you simplify this, we have 15 out of 56. Okay, we have 15 out of 56. All right. So that will be the chances of getting the first being red. And then what we do, then we have to add up the two values to get our final answer. Okay, we add the two values to get our final answer. So in summary, these are possible outcomes for their probabilities. The first being red and the second being red is 3 out of 28. The first being red and the second being green is 15 out of 56. The first being green and the second being red is 15 out of 56. And then the first being green and the second being being green is 5 out of 14. Let's see another example. Let's see another example to illustrate that again. Okay. All right, dependent and independent events. Dependent and independent events. So according to the definition of dependent and independent events, so two events are dependent if the probability of A times the probability of B is equals to the probability of A times probability of B. Okay. Right. So lastly, talking about the addition rule now, talking about addition rule for a mutually exclusive event. An example to illustrate that: a sample space X consists of all natural numbers less than 16. A sample space X consists of all natural numbers less than 16. A is the event of drawing an even number at random. B is the event of randomly drawing a prime number. A and B are mutually exclusive events. Prove this using the addition rule. A sample space X consists of all natural numbers less than 16. That means sample space we have elements 15 from 1 to 15. So A is the event of drawing an even number, and B is the event of drawing a prime number. Now, are A and B mutually exclusive? Prove this using the addition rule. What do you need to do? You need to write out our sample space and list out all the elements of A as well as all the elements of B. And then from there, we can now use our addition rule to see if the events are mutually exclusive or not. So now, for the sample space, for elements less than 16, we're going to have it from, so the sample space will contain elements 1, 2, 3, up to 15. And then A being natural, A being what? Even numbers. Event of pulling out even numbers, random selected even numbers. That will be 2, 4, 6, 8, 10, 12, 14. So these are the elements of A. Okay. And then for B, being events of selecting prime numbers less than 16. So prime numbers less than 16 are 2, 3, 5, 7, 11, and 13. Okay. Now the question is, are these two events mutually exclusive? So are they mutually exclusive? So to prove if they're mutually exclusive, what we do, we use the addition rule. We use the addition rule. So we try to prove that probability of A and probability of B is equals to probability of A and probability of B is equals to 0 for events that's mutually exclusive. But if probability of A and probability of B is not mutually exclusive, then they are not mutual. If the probability of A and the probability of B is not equal to 0, then they are not mutually exclusive. So looking at A and B now, you can see there's an element 2 here, there's an element 2 here. So there's an element 2, there's an element 2. So we're going to see that the intersection between the two events A and B is not equal to 0, meaning there are elements that are found in A as well as found in B. So that means the intersection between the events is not equal to 0. So that means the events are not what mutually exclusive. This means the events are not mutually exclusive. So because their intersection is not equal to 0. Otherwise, another way to do this is to compute the value of A only and B only, and then we can now see if they are mutually exclusive or not. So we're saying probability of event A is 7 over 15, probability of event B is 2 over 5. Right. And then probability of A or B. Let's find probability of A or B. Probability of A or B will be 12 over 15. Probability of A or B will be 12 over 15, meaning when you combine all of them together, you have 12 over 15 in all. Okay, right. So now, trying to use that to find our probability of A and B using our addition rule. Remember, our addition rule says what? Probability of A or B equals to probability of A plus probability of B minus probability A and B. So here probability of A and B is not equal to 0, and then we say it's not mutually exclusive. It's not mutually exclusive. So these two events, A and B, are not mutually exclusive. So another example we can look at today, probability that a person drinks tea is 0.5. Probability that a person drinks coffee is 0.4. Probability that a person drinks tea and coffee or both is 0.8. Determine the probability that a person drinks tea and coffee. So we use our simple addition rule to find probability of the drinking of tea and at the same time coffee, meaning the intersection of tea and coffee. Probability of tea is 0.5, probability of coffee is 0.4. Probability of tea or coffee is 0.8. So now, what is the probability of drinking both tea and coffee at the same time? So using our addition rule, we are finding probability of drinking coffee and tea at the same time, and then that will be 0.4 plus 0.4 minus 0.8, and that will give us 0.1. So probability of drinking tea and coffee at the same time is 0.1. Okay, and then the complementary rule. So in example, to demonstrate the complementary rule, Joe wants to open his tuck shop at his school, but he's not sure which cold drink to stock. Before opening, he interviewed a sample of learners to determine what type of cold drink they like. From his research, he determined that the probability that a learner drink cola is 0.3, probability that a learner drink lemonade is 0.6, and probability that a learner drink neither is 0.2. The probability that a learner drink cola and lemonade. The probability that a learner drink cola and lemonade. So now, how do we start off with that? So first thing, to determine probability of learner drink cola or lemonade. So now, let probability of drinking cola be PC and then of lemonade be PL. So probability of drinking cola is 0.3, lemonade is 0.6, and neither cola nor lemonade is 0.2. So that means probability of drinking cola or lemonade is 0.8. Because you had said the probability of drinking cola, the word not implies 1 minus probability of that very event. The probability of now drinking cola and lemonade is 0.8. Okay. So getting that, then can now use our addition rule to find probability of drinking cola and lemonade. And then using the addition rule, if you put substitute your values, then we're going to see that that will be equal to 0.1. Okay. And then determine probability that the learner drink only a cola or only lemonade. So we're going to see probability of only C or only L, because probability of C or L minus probability of C and L. And that's what we're going to do, and then subtract our values here, we're going to get 0.7. So we end the class here for today, and the next class we carry on from there. So please join me in the next class where we get more examples on Venn diagram. Thank you and enjoy the rest of the day.